Good morning, everyone. For me, it's a great pleasure to talk here in front of this audience of many colleagues that I work with and many other people that inspired my work. I will try to touch some of my work and also approach others people's work here. And I should thank very much Francois and Fiammetta for believing and organizing this. It's really a great pleasure. So the setup for my talk is very similar to what we saw, how we started yesterday with Vittorio Loreto. So we are interested in text. We have a text. We are interested in measuring things. For instance, the size, how many words are there, how many distinct words are there. We want also to identify some specific words and count them, to look at their position in the text, compute their frequency, how many times they appeared, perhaps normalized by the size of the text, and approaching also the ideas Francois mentioned yesterday. So on the back of our mind there is the idea of how to generate this text. I'm not talking about text generation, but I will talk about some generative models, some simple stochastic models that reproduce some of these features in the hope that is a step in this direction. So I think this type of problem is very old. At least go back to the Middle Ages when people were trying to encode, decode information. But I think it's from the 19th century on when people started to think about how to transmit information efficiently. People like Morse, that is famous now for this Morse code. And he had to know that the letter E was much more frequent than the letter Z, and so this encoding is more efficient than just a randomly encoding. So this is, I think, the time when these things started to be done more systematically. Correct me if I'm wrong, perhaps you would be interested to know when these things approach, but because what I'm really trying to approach in my talk is one of the main observations since this time, which is the appearance of these universal laws, or these features which are observed in many different texts, in many different languages. So perhaps the most famous one, already mentioned yesterday, is Zipf's law. So we rank the words according to their frequency, and the frequency of their appearances scales with a rank, an exponent close to 1. So we saw this picture also yesterday. So this is the work of Zipf himself. He's plotting here the rank frequency for 2 words. So James Joyce data, and another, this is the curve A, and the curve B is another completely different database than what he sees. So here is the number of words, it's not a normalized frequency. That's why you see this vertical mismatch. So if you imagine you would rescale things here, put these 2 points together, you will see that the 2 curves, A and B, would fall on top of each other. Completely different databases, same type of observation, and what he calls an ideal curve is just this alpha 1 exponent. Right? So this is, of course, repeatable to many other languages and databases. You'll see some things in my talk, but this is the essential universal. We think also about the talk yesterday. So this is a feature which is asking to be explained or explored. There are many more of such laws. We saw Hibb's law yesterday, so the number of distinct words scales sublinearly with the database size. I will come back to this also later. Coming closer to things I have done, the exploration of correlations in the text. For instance, if you have a string of letters and you make a very stupid encoding, let's say you code a 0 or as 1 a vowel and a 0 a non-vowel, you have this very stupid string of zeros and ones. And if you measure now the correlation, so the correlation between 2 bits separated by a distance t, so a time t, and the observation starting from the 90s is that this correlation scales also algebraically, so it decays as a 1 over f noise in terms as Theo Geisel was speaking yesterday. So here is just one measure that we did for this book, War and Peace. But I think it's important to look at this scale. So if we go at this scaling, which is different from the random one, the shuffled one. So we are talking here about correlations on the order of pages, right? So the origin of these long-range correlations are not the syntactic structures as how we build sentences, how we move letters or words to the end or to the beginning. We can discuss the origin of these things, but it's for sure this law and all the others here are not driven by syntactic rules of the language. So what I looked first. Yes.
By naming it like this and by plotting it like this, I guess you want to allude to some random, super diffusive random walk.
Exactly. So this is, yeah.
So are you going to comment on it, or?
I was not, but yeah. So I'm computing. This is just a way of computing. That's why I'm writing here in this strange way. It's just that the computation method. So you apply DFA and other techniques. So if you want just the two-point correlation, the integral of the correlation or the random walk built by this sequence, right? So if we now consider 0 is a step to the right and 1 a step to the left, and we see how this random walk diffuses, you can relate the long-range correlation to a super diffusion. And this is the super diffusion exponent gamma here, which is related by 2 minus gamma. This is just, but here is just a way of measuring this correlation. So I started thinking about these universal laws in our work with also Janet Pierre-Humbert, who is also here. And what we looked here was on the word level. This is our text, and we were marking where a given word, like Prince in War and Peace, appeared, and we see this clustering of appearances. And we were looking at the time between consecutive appearances. So if we compare this to a random process, so just a random appearance of words with the same frequency, we can see by eye this clustering. We can see also other words which by chance have the same frequency. The word so, for instance, which shows perhaps some less clustering. And what we came up was with the proposal that the distribution of these times, the distribution between the intervals of successive occurrence is not an exponential, is not a power law, but is well described as this stretched exponential. So it's an exponential distribution with a beta exponent. So if beta is 1, we recover the random case, but for different words, apparently we have a different beta. So the smaller the beta, like in the word Prince, a content word, it is more bursty or more clustering, while for function words you typically observe a smaller beta. So there are many more of these laws, and the names here, or except mine, of course, the other names are just the names as things that people know these laws. These were known before, right? So, but this is how we call them today. So the questions I want to address. So I think also other people, also in the next talk by Marcelo Montemuro, approach the same problems with different tools. So. There are many more such laws. The questions I want to approach here is, why are these laws important? Right? So, and are these laws true, or what does it mean law? What does it mean true? Right? So as I mentioned, it's not a syntactic rule. It's not the law in the sense of a syntactic law. Perhaps it's more like a stylized fact in economics. Can we violate these laws? For sure. Right? So now we saw also examples yesterday of texts that are written on very peculiar ways on purpose. So we already feel that there must be some truth. If there is anything true behind them, there must be some fluctuations, some stochasticity, some probability associated to these laws. This is the direction I'm trying to go. How rigid are these laws? As I mentioned, and are these laws related to each other? Are they independent? So here is the plan of the talk. I will give some general approaches to this. We'll focus on vocabulary size, and if I have time, we'll come closer to innovations later. So why are these laws important? Just very briefly, I think there are fundamental motivations. So the idea that if there is this pattern, we may, by understanding the origin of this pattern, know more about how text is produced, how language works, or how we think, how we express thought. As also from the discussion yesterday from Francois, it perhaps can be seen as a constraint on the freedom we have, on the creativity that we have using language. But perhaps I'll approach more in the talk practical motivations if you want to analyze text, you may need to take this into account. If you want to generate text, you want to impose these as constraints. If you want to extrapolate to unknown text sizes, to unknown corpora, to unknown languages, you have having a parametric expression that allows you to do that may be very useful as well. But I think, so the first question I want to answer, in which sense are these laws true or universal? And I don't have a definite answer, so the approach we have here is that we have now large databases. So can we do a better statistical analysis than before? So by large databases, here I will deal with the complete English Wikipedia. It is Google Ngram corpus, more than 1 million books in different languages, and all scientific papers published in these journals, which are available for analysis. So have to say that many of these laws were discovered in the sense of zip, not much more detailed analysis than what I just saw. You plot things in a log-law scales or with some transformations that they seem to scale in some sense. But I think this is by far not enough. Let's look at Zipf's law, for instance, in this Google Ngram corpus, the larger corpus we have. These are all books published in the year 1800. This is the rank frequency plot, and this would be Zipf's law, or the ideal dimension. We already start to see some deviations. If you plot the data for 100 years later, we have a larger database. We see that it falls more or less on top of the previous case. We just can go further because the database is larger. If we plot 100 years later, even larger. So we see these deviations, but we see this universality. We see that hundreds of years later, the same law is still valid. So what we did here is search for a generalization of Zipf's law. We went to the literature. We looked at all possibilities. We restricted to those that have only 2 free parameters. And we compared through a maximum likelihood fit, and when possible, some different statistical tests. And what we came up is that, as the naked eye suggested, but here is was a statistical analysis, that these sort of double power laws. So we have Zipf's law for short ranks and a smaller decay, a Zipf's law with a different exponent for longer ranks. So we can think this rank division here as a sort of a size of a core vocabulary. So there is a core vocabulary for Zipf's law, and there is a slower decay later. And this is our observation on different languages. This was consistently the best description of the data. What was changing from language to language, this was also mentioned yesterday, are these parameters. And we have some explanation essentially why the core vocabulary on different languages is different. This is also related to the lemmatization and filtering that we do in our data. So I don't want to enter in details here, but we can do that. So here for the English Wikipedia. Huh?
You couldn't read the parameters here.
The parameters, yeah. So, yeah. So essentially for German and Russian, you have a more inflection in the words. So we are not lemmatizing things to the root of the words, and that's why we see the parameter B is 2 times bigger in German than compared to English. So it's indicating that the core vocabulary is bigger. But well, I don't know if there is something much deeper into this we could discuss. So, but the core vocabulary here in English is around 8,000 words, in German 20,000 words. Let's say this is the place where this knick happens. This is what maximum likelihood is telling us. Okay, so this is another database, Zipf's law in Wikipedia. Here is just for comparison. It's a log normal or a power law with a cutoff, and we see if the fluctuations are much smaller for the double power law. Okay, so in these statistical sense, in which sense is this true? We could hope from this analysis, from this good agreement, that the data is consistent with the model. If you want now to assess make a significant test, and we say that these words are being sampled from this distribution randomly, and we calculate a p-value for that, we always find that this statement is not true. The data is not consistent with the model. And you can sort of understand that very easily because the database is so large. You have so many words that any small systematic fluctuation is significant. Right? So course, you can argue that in a small text it will be significant, but I would argue that this is just because your database is small. So if you had more data, you will see that they are not significant with the data. Or there are fluctuations, there are systematic deviations. And this has to, we have to interpret in this sense. The sense that they are true is that they are the best simple description. And they apply to different corpora languages with very small variations of the parameters. This is the sense where we can look at it, and we should not forget that deviations, fluctuations are typical. So I think approaching the other questions is better to look at a specific problem, and I will look here at vocabulary size. Coming back to Morse, we all know Morse codes, but actually his first approach to encode information was on a word level. So he was creating a dictionary of all words alphabetically arranged. So he gave up. Probably he gave up because there are too many words. So the question I just want to ask is how long would be this dictionary? Right? So how many different words would he has to write there to allow people to transmit information? Huh? Sometimes you find reports on the size of the vocabulary of a language. So this appears in the German press last year. The German Academy for Language and Literature released this data. The number of distinct words in the German language on different periods. And if you look at also this science paper that introduced the Google Ngram corpus, they have estimations for English also on different periods. So these numbers are not comparable with each other because of filtering and lemmatization, but the tendency is always that things are growing, right? So this is the message. But if you look what they did, so what is the role of database size? How are they normalizing by the different databases you have? And this is far from being clear. Another motivation for looking at the vocabulary are, for instance, the problem of constructing invert indexes. So if you are scanning the World Wide Web and page by page and trying to see which page has which word, building such metrics, adding more pages and pages, you don't know how many pages you have. You would like to know in advance what is the vocabulary size, which memory you should allocate in your program for this matrix. So you will need an estimation before how many different words do you expect to find. Other examples of application would be to compute the vocabulary richness of texts or authors that wrote texts of different lengths. So as we saw yesterday, the scale of the vocabulary size, distinct words as a function of database size, follows this Hibbs law, the sublinear scale. So I'm plotting here year by year. So this is a suggestion that things are growing. But things are growing just because we have more data, right? So if you plot for the Google Ngram every year, so you see they fall almost in a line. So each point here is all books published in 1 year. So if we just add all books together, we get 1 point here. If you get Wikipedia, completely different database, we get a point here. So apparently there is something to be explained. There is some of this loss that we could hope here. Something like Hibbs law. Here are the different languages. So I shifted them horizontally just for clarity, but they have similar scaling. So French, Spanish, Russian. So what is a good description of this data? Can we then that we can use to predict, right? So we see that there is a slight tendency to slow down. We could even hope that these things will converge to a real vocabulary, so it would make sense to speak about the vocabulary of a language. So the most basic approach here is just to relate this Hibbs law to Zipf's law, as discussed yesterday. So you assume that in a most simple case that the words are being used randomly with a fixed rate, and the rate is given by this frequency. So the Poisson here is not very important. What is really important is that the rate is given. It's a stationary process for every word. And so what we did, it is very easy. So if you observe the frequency follows this double power law that I mentioned before, we can compute this and compute an expression for the expected number of distinct words, which turns out to be again a double power law. So this relation between the Zipf's and Hibbs, which is known at least since Mandelbrot, is valid asymptotically now, as Vittorio mentioned yesterday. But in this case, we find this first regime can also be related to each other. So if we compare with the data, so we fit the Zipf's law and we compare in the Gibbs plot, we see these are the curves we get and provide a good account of it. So there is no convergence, right? So there is an asymptotic sublinear growth. So from my point of view, there is no sense in speaking about the vocabulary of a language unless you say how many words people speaking this language have spoken ever. Then you could get a point here and estimate a point there, but I would speak about the vocabulary in absolute sense, and it doesn't seem to make much sense. Okay, so one point that was also discussed yesterday, well, here it's a bit of cheating. I plug in Zipf's law, I get Gibbs law. Can we get something consistent? So this is, our proposal is a type of generative model. So we will go quick into that. But so the basic idea is that you have this idea of core vocabulary. You have two types of words, core words and non-core words. So if you write a text like with these rules, you can get both Zipf's and Gibbs law. So and the rules is, for each word, I ask, is it a new word? If it's, and there is a probability attached to it, I will come back to this later. If it's an old word, I will choose among the words that I already used proportional to their frequency. So this is the preferential attachment or rich get richer mechanism. If it is a new word, then I ask the question, is it a core word? And that is again a yes-no question with some probability. And the crucial aspect here is that the core vocabulary is finite. So at some point I will exhaust this path, and I can go only on this path, while the non-core is infinite. So the probabilities here, there are two free parameters only in the model. One is this probability of being a core or non-core. Well, one is the size of the core vocabulary. So this probability PC is small when there are still core words to be used, and it's zero otherwise. So the two parameters in the model are the size of the core vocabulary and how this probability, the probability of using a new word, is reduced every time I use a new word or every time I use a core word, reduced by parameter alpha. So alpha and the core vocabulary are the two parameters which we can relate here. Let's see the details with these two parameters of the Zipf's law and of the Gibbs law. So the other question related to this Gibbs law observation is that what are the fluctuations? What are the error bars in your estimation? So I have this law, I know this scaling, how sure I am about this? What is the, if I have to estimate the vocabulary, can you give some confidence interval into that? So we went to data. So this is the Zipf's relation now for the Wikipedia. So each dot here is an article in the Wikipedia. But we could also construct the Gibbs law for each article, right? So as we mentioned yesterday, we could just go through the text and see a line for each article. And what we see here is the Poisson prediction, and this is the data we observe. And now if we do a smoothing, or let's say a running average in this plot, we see here, let me go. This is what we get. So we already start to see that there is a bias, a systematic deviation here. But what is more interesting is that you see that the fluctuations here are very large. So if we calculate the expected fluctuations from the Poisson process, random sampling, we get these error bars, let's say, which probably you don't see much, but they essentially vanish in this region. While the data shows much more fluctuation. Yeah, the colors here are not very good, but the fluctuations here are much larger than these ones. So to characterize that, what we did, we computed the fluctuations for a given text length, the fluctuations we observe in the data in this direction. So we computed the average value and the standard deviation. And if we plot this standard deviation as a function of average value for different n, the Poisson process predicts a scale with the square root of the mean. This is central limit theory. And what we observe, this is the smoothed data we get, is a linear scaling. So in physics we will say that this is a non-self-averaging quantity. So the relative fluctuations, the standard deviations, do not decrease by increasing your database. So the fluctuations remain always on the same order as the mean. It's a completely different type of scaling than you would expect from this Poisson process. So there are two deviations that we observe. The first deviation is a systematic reduction in the expected vocabulary, and the second and more relevant one is a different scaling of the fluctuations in the observations. We repeated this to the +1 database, to the Google Ngram, and we systematically see this deviation. And so how can we understand these observations? How to understand these deviations? So the first thing I thought was, well, there are temporal correlations. We know there are long-range correlations. So what we did is that we constructed now lines, as I mentioned in the Hibbs plot, for each article in the Wikipedia or in +1, and we shuffled this and computed things again, and we observed the same thing. So there are correlations. We are not capturing it in the Poisson approximation, but this is not the main origin of these two observations. So temporal correlations inside a text. So our approach is to describe this as a fluctuation in terms of topics. It's rather trivial, but once you think, but it's nice to see that you can explain this quantitative scale. So the idea of topics or topicality is obvious, is that words do not have the same frequency in every document. They vary depending on the topic. So for instance, in this +1 scientific database, we take the word network. In the overall database, it ranks 428, has a given frequency. But if you do document by document and compute the frequency inside each document, of course, it has a huge variety. There are papers about networks where the frequency is perhaps even 10%, but there are many papers that are not about networks. So you have a fluctuation, it's a logarithmic scale, very large fluctuations around this value, which are reflecting the topical aspects of the text. So topic here is understood as a hidden variable that is controlling this fluctuation. So formally, a topic will be given by a list of frequencies of the specific words. So if you think about a topic, or if you have a family of topics, the model I'm trying to come here is that if I choose one topic, the frequency in the document will be given by this. So if I choose this red topic 1, I use it as a Poisson process, right? So I don't want to touch this now. So in this document, this word network will appear very rarely. If I choose another topic, the word will be appearing much more frequently. So if we now want to calculate the expected number of different words in a database, we have to make a double average, an average over the Poisson process as before, but also an average over J here, which will be the choice of topics. I have to say how I choose the topics. So the Q here indicates that this is a quenched average, right? So because it's for a fixed topic, we compute the average. So we get this result, which is smaller than the previous results, which is an annealed average. So this is the average of the exponential, and this is the exponential of the average. So this is essentially explaining this deviation I observed. So this is what we expect from a simple Poisson model, and this is what we expect from a Poisson model with topics. And this is smaller than this. So this is the first observation. We can repeat the calculation for the variance, and we get the same thing as for the Poisson process, but we get a covariant term here. So this is measuring the correlation between different words. So, and you can imagine in a topic like networks, you expect that other words related to network will appear also more frequently. So the correlation between different words is not vanishing. So, and this term will scale as the database size square, and this explains essentially this anomalous scaling of the fluctuations. So if you want to be more quantitative, we have to specify the topic model. We have done this for two specific models, just to convince you that this is indeed the explanation. So one topic model, if you wish, I just get in my data the frequency on each document, and I use these frequencies. I say each document I'm drawing, I draw a frequency for the words. This is a bit cheating because you use the data you want to fit. Another topic model we used is this latent Dirichlet allocation, which is a famous machine learning method to extract topics from the data. As an automatic topic extraction, essentially you have two probabilities, the number of topics in a document, and this is drawn from a Dirichlet distribution, and the frequency of the different words in a topic. This is one example. This is for a given document. You see here that these are the representation of the different topics, let's say 20 topics. There are only 3 or 4 topics which are represented in this document. This is the outcome of this method. And the frequency of a specific word, let's say the word network, is represented in some topics, in other topics not. Okay, I don't want to enter into the details of the method, we can discuss this later, but if you apply these two methods here to the data, we observe. So this was the Poisson as before, the blue one. The data is in orange here, you can hardly see, but in the real frequency we reproduce almost exactly the curve here. This is the Hips plot, and for the LDA, it's already in the right direction. And more important is fluctuation scaling relationship. In both cases, for these both methods, they scale linearly with the mean, as in the data. So this was the observations, the modeling we do. We try to approach some applications or the implications this to a real problem. And the problem we are considering here is how to measure vocabulary richness. If I have, for instance, 2 texts of different length, 2 authors that have produced different amounts of text, how can I quantify which one used more words, which one has a richer vocabulary? The traditional approach from 50s, I think, is to compute this Herden's constant, which is just taking the ratio of the logarithm of the number of distinct words over the database size. So this is essentially the same as Hips law. You assume Hips law, you compute the ratio of the logarithm, this is the exponent, and this is how you compute it. So there are problems here, right? So first there are deviations of Hips law, as I mentioned, so this double scaling aspect, and there are these fluctuations. So what we think is as a general approach is to compute the probability of having n words given a database of size n for a given model, a given topic model, for instance, a given generative model, and then just compare the quantiles. So I am in the 1% quantile, you are in the 5% quantile, so I have a richer vocabulary than you. In practice, one way of doing it as the simplest way is to assume that the fluctuations are Gaussian. Then we can take our linear scaling between the standard deviation and the mean. The prefactor is describing well the data. So we can compute now the quantiles of the z-score as a deviation. How many sigmas are you from the average behavior? So plugging this thing in, this is the formula we get. And now for the average number, we just use our double power law from the fit. And we can add topics here. This is the very simple approach. We have these numbers here from the fits. We have our topic model fits, so we can compare data. Let's see how it looks like in our real data. So we looked again at the Wikipedia data. So this is the vocabulary size as a function of length. We now normalize by the expected number, so just to have a flat expectation, so independent of vocabulary size. So this is our data. If you would apply this Herden constant, C, I'm plotting here the lines where you get the same Herden constant, right? So if you go to this line, according to this measure, all these texts have the same vocabulary richness. And you see that there is these curves are increasing. So there is a bias towards smaller text. So a smaller text is rated here having a richer vocabulary than a larger text. So you see that there are very few large texts that have this constant, while there are many that have this constant. This is a sign that this is not a good measure. Indeed, the richer article is, according to this measure, is this one, so which is a very small text. So if we compute our approach, the z-score, with no topics, you get a bit better. So the lines with the constant score are less biased, but still very biased. While if we include topicality also in the model, we see that this becomes significantly better. And in particular, the richer vocabulary agrees with the data, the computation of the richer vocabulary. So showing how it is important to take into account not only the correct Hipps law, but also account for the fluctuations in this application. So this is what I had to say about the vocabulary size, and I have now two smaller things to say. If you look back, the root of what I did here was essentially having these two old laws and trying to combine them. And when we try to combine them, we see that we need modifications. There is another law, if you wish, or another scaling relationship, which is this fluctuation scaling. So I think this is an insightful way of proceeding, of trying to see how these laws are connected, how can you relate things. And this is one way of seeing also what the work I've done also with Giampaolo Crisadoro and Mirko, who are here. We are trying to connect the temporal aspects of the text, for instance, trying to connect the correlations with this recurrence times. So you remember I was arguing this long-range correlation aspect of the text, and I was arguing for these waiting time distributions. And what we proposed essentially was that here we are looking at the text as a function of the letter. Here we are looking at the text as a function of words. How are these things compatible? Are these things somehow related to each other? And we essentially propose, and not go into the detail, on an explanation of how can you observe, let's say, if you encode your text on a vowel consonant level, is what I did here, or if you look at the text at the level of words, as we are looking here, how by adding sequences like this, you can still observe long-range correlation in the low level, while you cannot observe this clustering on the low level. So in some sense, it is explaining how a correlation or a burstiness on the function words here can translate into long-range correlation when you do a stupid encoding like a vowel consonant. Not entering in the details, but this is also an idea of taking these two laws, trying to see how they match together, how can you accommodate them together. And the last part of the talk, I just want to say the things we are working on, innovations. If you speak about vocabulary and how everything is the same, it appears that nothing is changing. Of course, something is changing. This idea of the core vocabulary, for instance, we have this Google Ngram database. If you look, the distribution is not changing, but if you look at the distributions of which words are more frequent, they of course change. So for instance, in 1900, we had words like majesty, Napoleon. Yeah, so Napoleon is still somewhere here, so, to use your terms. And now you have different words. So what we measure is now, if I look at the core vocabulary I identified, so the most frequent, the 8,000 most frequent words in English, and I look after a given time interval, after 50 years, after 100 years, how many of these words are still there? What I observed for the 1905 is this curve. It's quite well described by an exponential. So these are for all years, so you cannot see, but this is roughly an exponential decay. What is interesting is that if I compute now the rate of decay of the core vocabulary, the rate of replacement of the vocabulary over the time, this appears to be increasing. So there is
this is Google Ngrams?
This is Google Ngrams, yeah. So it appears that the size of the core vocabulary is not changing much, but its composition is of course changing, and it is changing on a rate of about 30 words per year. And this rate is slightly increasing over time. So this message that the vocabulary is growing and it's everything increasing, well, I don't see statistical significance on that because database is increasing, and it's very hard to normalize for that. It's perhaps possible, but what we observe here is that the vocabulary the change is increasing in another sense. The replacement is becoming faster. So just for example, in 1900, these are words that are now that were in the core vocabulary and are not anymore. Majesty, so you see some obvious things, Napoleon, majesty, but there are also non-obvious things like doubtless and furnished. And these are words which entered in the core vocabulary, like cultural, computer, environmental. So the last thing I want to speak about, also because I think Richard Blythe is going to talk about this two talks. So it's vocabulary replacement, right? So, and very simple thing we looked at these databases, for instance, how do you write Kolmogorov in English or in French or in German? Could be Markov also. So and there are different ways of writing the ending. You could write with a V, with a W, or with a double F. And if you look at this Google Ngram, this is English. Historically, over time, so these are the blue dots, we see this type of behavior. Around 150 years ago, the V choice was rare, and now it is unanimous almost. So this is an average over many, many names, not only Kolmogorov. So, and what you see here is this type of S-curve. Right? So, and this is another of these universal laws which are stated. So language change happens through an S-curve. It starts slowly, accelerates, and slowly. So we looked at other databases. This one is fun. It's the German orthographic reform. So how it was a proposal replacement in 1996 of this strange beta-like letter, so the SZ, to a double S. So we looked at all words that changed, were affected by this rule, and we see here that indeed it was moving towards the direction we proposed the academy. But the fun thing we learned is that actually in 1901, so 100 years before, there was another reform that was essentially changing all the words in the opposite direction. And the fun thing is that the previous reform was much more effective, so it took place much faster than the new reform. Right? So apparently every 100 years they decide to change their rules and how we are supposed to write. But it's also interesting that
the obedience is less than it was 100 years ago.
Yeah, there was a huge opposition, yeah. So the newspaper made a strike and it went to court and the Supreme Court had decisions. Yes, perhaps we live in a society where we can oppose better than in 1900. But what the questions we were, so another case of course, also the classical case of regularization of verbs, where here is the case of the word, the verb spill, that is becoming regular over time, and here is also a fit. So the questions we were asking here, are these S-curves we observe here universal after, let's say, a rescaling? Or how much information is there? And the answer we found is that no, the shape of these curves are not universal, and there are some information you can extract from it, especially whether there is an external forcing on the change or if it's happening endogenously. And I will refer to the poster from Martin about this topic. So that's what I had to tell you. So let me summarize. So I started with some thoughts about universal laws. There are systematic deviations, but more important, there are strong fluctuations on these laws. So if you want to impose them, if you want to a text generation, I think it's not a wise idea to impose them rigidly or to impose them strictly. So an approach that I was suggesting is to try to connect these laws to each other. In the specific case of the Hibbs law, we are able to explain these fluctuations and the implications of this based on this idea of topicality or topic models. And finally, I mentioned this non-universal aspect of the S-curves. And let me, at the end, thank all my collaborators that were here. I already mentioned also, but my group in Dresden, and especially Martin, who is here, and will be in the poster session, and that helped in this heroic effort of submitting these 2 archive papers by Tuesday night, just before we left here. So it's excellent to have a deadline, and it was mainly to his work that this was successful. And so let me thank you also for your attention.